So today we're going to focus on notation, the way we write about sequences, particularly writing rules for arithmetic and geometric. The first thing we need to understand is the difference between sequence notation and regular notation. Sequence notation tells you that it's a sequence, and remember, a key thing about the sequence is that it has inputs that are counting numbers 1, 2, 3, 4, 5, 6, 7, not 0, not -2, not 1/2. Sequences are limited to inputs that are counting numbers. When we look at what the T tells you, and by the way, it can be written with a parentheses or it can be written as a subscript like this, but T of 4, that just says, what is the value on term 4? So we would look in the sequence and say T of 4 is -2. Or we could look at the sequence in a table form and say T of 4 was -2. So that notation just says, what's the output when the input is 4? Okay, we use that sequence notation with the n and the t of n to focus specifically for when we have sequences versus functions. So we have here a table, though they don't look that similar, they actually have the same rule. The t of 4 here is going to be -2. The fourth term has an output of -2, and f of 4 also has an output of -2. The difference between the t's and the f's is that with a function, the input can be negative. It can be 0. It can be fractional or decimal. And then it can be a counting number like 1 and 4. So these two tables look very different because I've included the negative and the 0 and all of that stuff, but they have the same rule. And this particular one, because it's a sequence, has only inputs that are whole counting numbers, but it's -3 times the term number plus 10, and f of x is the same thing. It's -3 times whatever your input is plus 10. So if we look at 4, -3 times 4 is -12, plus 10 is -2. Sure enough, it has the same input and output as in the sequence notation. But the key is, idea one more time, sequence notation indicates it's a sequence, and sequences have inputs only 1, 2, 3, 4, 5, etc. So when we're writing explicit rules, today, right now, focusing on arithmetic, you're going to use what you already know about y equals mx plus b or f of x equals mx plus b. The f of x stands for the total, the m stands for the slope, the x stands for the input, and the b stands for the y-intercept. It stands for the slope. How it grows, whoops, slope. The same thing is exactly the same for arithmetic. You're looking for two pieces of information to allow you to, depending on what your input is, find your output. So the two pieces of information we need for a linear or arithmetic are what's our 0 and how's it growing. So here we are looking for how is it growing. And we need to find that 0 term. I'm going to do that by going backwards. So there's two ways to write an explicit expression, explicit occasion is. One is to use what we know, which is a 0, and the other is to use the first term we're going to talk about in a second. So here's term 1, here's term 2, here's term 3, here's term 4, and we can notice that the generator, or this is arithmetic because it's dropping by 3 each time, and that is going to give us our m. And then we have to go back to the 0 term. If it's dropping by 3 moving forwards, then it's going to add 3 moving backwards. So 15 plus 3 is 18. So now we know the 2 pieces of information we need. We found our B and we found our M. So we're going to go ahead and write it as T of N. The output when N is T is going to be 18 minus 3 times the term number. And that's this, you can also write it as negative 3 times the term number plus 18. Both are completely acceptable. So when there's another way of doing this. If you don't want to go backwards to the zero term, we can use the first term way. So you just take your first term. I want to find the output for any term. I'm going to start with my first term, and I'm going to go ahead and as well. Oh, this is a subtract 3, excuse me. I'm going to use that same slope. But if I put, like, let's say I wanted to find the second term. If I put 2 in there for n, I would get 15 minus 3 times 2. I would get the third term's information. So I have to go to the one before it. So instead of n, when I'm using the first term, I use n minus 1. You still need your slope, and you still need your information about one of the terms, but you can use the first term and then just tell it to go backwards 1. Okay, recursive formulas are actually the way we tend to talk about sequences. So in this particular one, we'd say it starts at 15 and it's growing by subtracting 3 each time. And so the notation that allows us to do that takes into account when we have t of n, that means the term we're talking about, and t to the n minus 1 means the one before it. So a recursive formula just takes what we know. We know that the first term is 15. And we know that we can generate the term, any term we want, by taking the term before it, n minus 1, and in this case, subtracting 3. So this t to the n minus 1 just means the one before it. Nice spelling. So the recursive formula, it looks confusing, but it's just saying, I know what my first term is, I know how it's generated, I can find any of them. So here, if we are looking at this particular arithmetic sequence, it is dropping by 4. And if we want to use the 0 term, explicit formula, we're going to go back, and since it's dropping by 4, we're going to add 4 to negative 8 to get us to the 0 term. And so we'd have t of n equals negative 4. That's our starting amount, and it is our growing amount. So it's going to shrink by 4 for each term. That's our 0 term way. If we're going to go ahead and use the first term form, all we have to do is start with our first term, in this case, which is negative 8. And we're going to subtract 4 each time. But we've got to tell it to go 1 back, because otherwise it'll be wrong. And then the last kind is recursive. And the recursive is just how we talk about this one. We're like, okay, it starts, the first term is at negative 8, and it grows by taking the one before it and subtracting 4. Now our equation for geometric, this one right here, up here is geometric because it multiplies by 2 each time. Geometric ones multiply or divide by the same number. And so our general formula is a times r to the n. When we get to more exponential functions where it's not just a sequence, it'll be a times r to the x equals f of x. And we use r in our class because r stands for multiplier rate. If you look in a textbook, it says a times b, but I don't like to use b because b has been standing for the y-intercept for so long. So anyway, a stands for your 0 term. So if we're going to go for the 0 term way, we're going to go ahead and shrink back again, or flip back to our 0 term to find a. R is what we're multiplying by, and n is our term number, and T of n is our total. So here we've got -8, -16, -32. We can recognize that it's a multiplier of times 2. And if we use times 2 going forward, we're going to divide 2 to get the 0 term. And -8 divided by 2 is -4. So if we're going to use the 0 term form, we're going to go ahead and say T of n is -4 times 2 to the n. If we're going to use the first term, we're going to go ahead and start with term 1, 2, 3. We're going to start with term 1, which is -8. So we have T of n equals -8 times 2, but we have to go backwards 1, because otherwise it'll be 1 off. And then recursive, same thing. We know the first term, and we know how it grows. So we say the first term is -8, and we can find any term, which is T of n, by taking T of n minus 1, which is the one before it, and multiplying it by 2.